Welcome back. Before the break, we looked at ways in which scientists record information, and we saw that information can be recorded in a diagram or in a table. But a far more exciting way to display that data is in a graph, because a graph is a picture that shows the relationship of two variables placed against each other, and you can generally see a trend much more easily. Is there a rise, a fall in the data? And that gives scientists a very good clue on how to draw their conclusions in the scientific method. So let's have a look at the first kind of graph, possibly one of the most common kinds of graph that you will experience in the life sciences, and that is the line graph. Here's an example of a line graph, and we're going to look at the various different components that make up that line graph. We've got two variables. One variable on this graph is the carbon dioxide concentration, and the other variable is time. The dependent variable should always be on the y-axis. And we know, therefore, that the independent variable is on the x-axis. Now, let's take a few steps back and work out what is that dependent variable and the independent variable. The independent variable that is going to go on your x-axis is the variable that the scientist controls. Now, the scientist on this particular graph is in control of time. The scientist has decided that he or she is going to measure time and plot a very careful scale of time, and then is going to find out, and that's important, the unknown variable, the variable that the scientist is going to find out, must go on the y-axis, because that is what we call the dependent variable. So remember, independent on the x and dependent variable on the y-axis. The axes must be labeled and units must be given. For example, parts per million, years, minutes, hours. Because the graph is a diagram, there must definitely be a heading. And that heading, it's very important to note, must reflect both variables. That's very important. So this graph is not just a graph showing the concentration of carbon dioxide. It must be the concentration of carbon dioxide over the last 250 years. We must take into account both variables, and of course the heading must be underlined. Each axis must be drawn with a ruler. Please don't infuriate your teacher or the marker of your exam by just scrawling it with a pencil and hoping that it's straight enough. Draw it with a ruler, because in that way you'll also be able to form a scale. You'll be able to divide your line into centimeters or millimeters, whatever scale you've chosen, and then of course you write the labels on the graph's axes itself. You then have to plot your points, and you would obviously read off the x-axis and the y-axis, and you would make points which you then join with a very nice smooth line. Be careful of making lines that look like that. Draw it with a nice smooth line. And the other important point is that you do not take the line beyond the known point of information. That is called extrapolation. You don't automatically start at 0 or start on the y-axis. You start at your first point of information. Often, a question based on this graph, a data response question, will ask you to predict what you think is going to happen in future years, and very often you draw that with a dotted line to show that you don't have the information, but you're making an educated guess. Draw those axes in pencil and the line of the graph in pencil, label with a pen, and of course if you have more than one graph, possibly you wanted to show carbon dioxide concentration and maybe carbon monoxide concentration, you would use a different color or a key to distinguish those two lines on the graph. Here's an opportunity for you to see another graph, also a line graph, we've got the birth mass, and then for the next few months of a little baby. How do we plot this information, and what is it going to look like? Well, that is what our line graph looks like. And I think you can see here very clearly, if we look just at the table, we wouldn't be able to pick up that there was a problem with this little baby's growth rate. Whereas when you convert that information into a graph, you can see most definitely that that little baby got sick around about 4 months. Graphs are very important, and when you look at the information that you have, you need to be able to distinguish between something called continuous data and discrete data. And this becomes important when we look at the bar graphs, because continuous data is numerical and it's going to follow a continuum in terms of mass. You can get 1 kilogram, 1.2 kilograms, 1.5, 1.7, and so on. We can have fractions of the continuous data. But when we look at discrete data, we know here that we're looking at things that there are no fractions of. You cannot, for example, have red and a half or Gauteng and 3/4. These are whole entities, and they need to be described on a very different kind of graph. A line graph, because you draw a line, indicates a continuum. When we look at discrete data, that we cannot do. So after the break, we will look at how we deal with discrete data.